So once you start develop your own project using RISC-V device, and you will have the opportunity to go through the kernel crashes. And because during of the bring up task, it is common to see that your device driver crashes for long device tree property. So in this video, you're going to see how the fault handler will be called in Linux kernel. In the first step, and you're going to see the symbol that is called handler exception. This is the name of the label that is trap handler in Linux kernel. This is the name of the trap handler. The name of this trap handler is the handler exception. If you go to this file, and you're going to see the body of this label. What I mean is that whenever the trap occurs in your system, the parent counter will jump onto this address, because this is the trap handler in a Linux kernel. And what that trap handler does is to read the highest bit of the supervisor course register. If the highest bit is 1, it means that trap occurs due to interrupt. If the highest bit is 0, it means that this trap happens because of execution of assembly instruction. So this workflow show you the exception occurs in Linux kernel. And after the value of the supervised course register is read by in the trap handler, it will jump to the corresponding the fault handler. This handler is defined in this file, and based on the value of the supervised course register, branch to this function is made. If the trap occurs due to execution of the equal assembly instruction in the user space, then do trap equal u function will be called. But if the trap occurs because of page fault and some of the invalid and address, that is misaligned address, and it will, and call to this function is made inside handler exception. This is the third step. So if you go to the definition of this symbol, you can see that this symbol contains the list of the callback function. This function can be called from the handler exception function. And in this case, and this workflow is made based on assumption that the memory overwrite occurs in your system. In this case, the call to page fault is made. And inside the page fault, you can see that the I function will be called inside the I function, and you can see that those kind of the API is called to the print the module that is installed, and it will print the set of the general purpose register and the control status register. And later, after it print the critical debugging information, the panic function is called. So now that you get to know the general workflow of the trap operation due to exception, let's take a look at this kind of the exception back to table. This symbol is exec vect under table, and this can be identified using trace-return debugging program. As you can see, this command is used to print the memory content starting from this symbol, and this is an option to print the memory contents in the symbol format. And here, this is the information that is observed in the binary dump. So another interesting thing is, whenever you wanted to analyze the trap handler or fault handler Linux kernel, and first thing you have to do is to refer to the manual of RISC-V architecture. As you can see, if the highest bit of supervised cause register is 0, the exception, a trap happened because of the execution of the instruction. If the highest bit is 1, the trap happened because of the interrupt. Now, let's take a look at another interesting workflow when the equal assembly instruction is called in the user mode. In the RISC-V architecture, we have the two separate the privilege mode. The first one is user mode, and the second one is a supervisor mode. When the equal assembly instruction is performed in the user mode, trap happened by the RISC-V core at microarchitecture level. Like another trap, running equal assembly instruction will trigger trap. Another thing you have to understand is that before equal assembly instruction, you can see that A7 register is updated. The reason is A7 register used as the storing the system call number. So every time you look at the equal assembly instruction in user mode, you're going to see the assembly instruction to manipulate the value of A7 register. So after running equal assembly instruction, you're going to see this kind of workflow. After the handler exception, handler is called, the function to the do trap equal u will be called based on the value of supervised cause register. Later, you will access syscall handler, and by using this syscall table, then based on the value of A7 register, because A7 register has system call number, by using this information, the corresponding system call handler will be called. But if the system call number is write system call number, this kind of write system call handler will be called. If the system call is about read system call, and at this stage, the sysread system call handler will be performed. Later, an internal kernel API will be called, and then we'll perform necessary operation for the system call. So this is a basic operation when you think about system call in Linux kernel. So system call is a terminology in operating system, but important thing is system call can be implemented using the feature of CPU architecture. What I mean is, if your system is based on ARM architecture, system call can be implemented using the feature of ARM architecture. In this case, SVC assembly instruction will be executed in exception level 0. In this case, X8 register will hold the system call number. But this is a scenario in the RISC-V system. For this reason, system call number is stored onto A7 register instead of, as with the assembly instruction, equal assembly instruction is performed in RISC-V architecture.